So we have a system where the input is u of t, right? And output is y of t. So we are trying to get this model here. Like when we give an input u, what is that response y of t of a system, right? So to do that, we will start with something called Lagrange's equations. Have you guys heard of it? Anybody? No? So this is a simple way of modeling mechanical systems, okay? And it's very like when you have complicated mechanical systems like two-arm robot, right? So it's very useful in modeling mechanical systems which have multiple parts, and you are able to take care of different constraints imposed by one part on the other. Okay, so that's what we will do. So that's one thing that we will do here in today's class, and then we will take some examples. For example, there will be a Twocar problem. Okay, and then we will do a inverted pendulum on card problem using same Lagrange's equation. Again, this is not the only method to model systems to derive equations of motion. When I say equations of motion, means we have a physical system, and then we are trying how that system behaves when you give a input to it, right? So inverted, and I'm terrible with handwriting, right? So we'll be posting type notes as well at the end of the class. But some of the things that you want to take care of, my R, I'm from India, so we had Britishers there, they spoiled us. So my R is this, okay? So I just want to make sure. Inverted pendulum. And then we will move on to state space modeling, okay? So these are the three things, and then following we will do a MATLAB implementation of this. So of the inverted pendulum example, okay? So that is the kind of goal, maybe today or I think it will take 2 classes today and Friday to finish this up. And this will give you a brief kind of a overview how we will deal with each of these systems that we will be dealing with later on, okay? So having said that, so this is maybe, how do you guys feel about exams? I was thinking of getting rid of the exams. I couldn't wait. So that, but there is a flip side of that. Yeah, I'm thinking maybe so right now our course weight is, if I say homework assignments, because this class is kind of a workshop. We'll be doing a lot of hands-on modeling, simulation kind of thing, and I have given a lot of exam in my life, and things that I remember today are the things that I have done something with my hands or something. But exams were okay. One night before I could, what are the definitions and all. But if we do that, then homework, I'm saying, might go to 70% of the grade. And that means it's serious stuff, right? It's really serious stuff. And then let's do just simple, some kind of midterm of 15% only. Just simple quiz on some kind of math concepts, because I cannot test you on coding and all in a class setting. And then maybe a class project for 15%. Is that okay? But beans, you will have to work hard for assignments. Like these assignments will be like design projects, and you will be doing a lot of coding. But the thing is, like, nobody's sitting on your head and say, hey, within 1 hour, give me an answer or something. You have a week to do it. You can discuss with friends. You can discuss with us. So I was thinking we can change that. And did you guys, anybody bought book yet? Don't buy it. Yeah. I just took a look at the book. I spent $110 and I don't think that's well, I'll post everything you need. If you still want to buy it, you can keep it for a reference, but yeah.
I'd just like to say, I think that you're going about your first undergraduate class pretty well right now.
Okay, so don't buy the book. I don't think I'll post all the related material needed from the book. Okay, so that's good. So then that's settled. Homework 70%. So that means I can demand more efforts in the homework. Okay? Great. So let's start with the Lagrange equations. Okay? So some advantages. It's useful for deriving, so some pros for that. Useful for deriving equations governing complicated mechanical systems. Okay, doesn't matter. You can derive a quadcopter equations of motion from it, multi-arm robot equations from it, a pendulum on the cart equations from it. So kind of again, this is not the only way to derive equations, but a good one. Okay, and the output, the equations comes in the form of differential equations. So what the resultant equations will be differential equations, right? Differential equations relating your input u to the output. Okay, so they will be differential equations. Okay, and then another one is it automatically incorporate constraints imposed by different systems. So you have two arms, right? For example, in a multi-arm robot, this arm imposes some constraints on this arm also, and vice versa. So this method has an automatic way of incorporating those constraints in the equations of motion. Okay, so there is only one drawback for this. There is a drawback, and it will be clear when we do the example. There is a drawback here that it needs generalized coordinates. Sometimes it's very hard to figure out what for a particular system what those generalized coordinates will be. And don't worry about it. We'll take the example too. So drawback is sometimes it is difficult to identify generalized coordinates. Okay, so that's the drawback of it. So let's discuss generalized coordinates then. Generalized coordinates. We represent them by Q. Okay, so let's say, so generalized coordinates are generally degrees of freedom, right? Like if you have a body, so what are the different degrees of freedom, independent degrees of freedom your system can have? Okay, and they are represented by a vector. Everybody knows vector in this class, right? Okay, so a vector Q1 to QR. So let's say we have R different degrees of freedom for that particular system. So we have to identify them and choose them. Okay. So which completely, these degrees of freedom, these Q1 to QR should incorporate like all the unique constraints to the system, okay? So that's our, remember then these are R, and then the next step, so that's the first step, most important step. You figure out what are the generalized coordinates of the that particular system that you are trying to model, right? And the second one, the next step is to get what is the total kinetic energy in the system, okay? So there may be different moving parts in the system, so you basically sum up total kinetic energy. So that's kinetic energy, okay? And the third is potential energy. So you also come up with what is the potential energy of the system, okay? Total potential energy, okay? And then we define our Lagrange's function, which is given as Lagrange's function, which is given as L. We denote it by L, and it's given as T. T is the total kinetic energy, which is a function. Again, kinetic energy is a function of Q1 to QR, right? And also the velocity is Q1 dot to QR dot, right? So Q1 is the generalized coordinate. You can always find a time derivative of each. So that minus the, again, I could have just written T as well, right? So don't get confused by, T is a function of Q and Q dots, right? And your potential energy. So it's basically difference of kinetic energy and potential energy is function of these, okay? So once you get that, your equations of motion basically can be derived as follows. So you take a time derivative d by dt for each generalized coordinate, a partial of L, which is the Lagrange's function, right? L is the Lagrange's with respect to each qi dot. So when I say I, this I is equal to 1 to R, right? 1 to R. So for each generalized coordinate, we will have to find the partial and take a time derivative. Then again a partial with respect to qi equals to qi. So this you guys know, but this is called generalized force or generalized force. So generalized force basically includes both forces and torques, right? So torques are a Newton meter, and so not just the forces, but also angular torques, okay? So this should give us a differential equation, which is basically connecting the parameters, which are generalized coordinates, to the input, which are the forces. Okay, it will be clear from example. So let me take an example first. Questions on this? Like, I have just giving you details here. So, okay, so example is a two-car problem. So we have a, let's say, a two carts connected by a spring. Okay? Right? So the cart 1 is Z1 distance from the origin, which is this line here. And cart 2 is Z2 distance from the origin. Okay? and the spring constant of the cart is K. So that they are attached with a spring. Okay. So, and let's say each cart we can put a force on it. Okay. So, or acceleration mass in F2. Okay. So that's the system in hand we have. So inputs for sure are, what are the inputs to the system? Two forces, F1 and F2, right? And Z1 and Z2 are two degrees of freedom actually, because they can move independently of each other, or we can change Z1 and Z2. If I have to choose my generalized coordinates, it will be Z1 and Z2, right? So let's say I want to choose, so now I want to find a relationship between Z1 and Z2 and these forces. So it's a multi-input, multi-output problem, right? There are two inputs, more than one is multi, so two inputs, and there are two states. Yes?
Is there supposed to be something after those F1s and F2s in the matrix?
Oh, you didn't see that. Okay. So let me write it here then. U of F1 and F2 just. Okay. So it's a vector. It's a multi-input system. So now let's apply Lagrange's equation to see what kind of relationship we get here. Okay. So let's choose Q equals to Z1 and Z2, right? That's the obvious choice of generalized coordinates. These are the degrees of freedom we have here. Okay. So okay. So once we do that, then we can go for total, find the kinetic energy. Kinetic energy for this, that will be T, and kinetic energy will be for the mass of this is M1 and mass of this is M2, mass of the cart, right? So we can say kinetic energy is basically depends on the velocity. So first will be half M1 Z1 dot squared, right? So how fast that cart moves, which is Z1 dot is the velocity of cart 1 and Z2 dot is the velocity of cart 2. Right? So that will be, total kinetic energy will be, again, using a Lagrange here is an overkill. We can simply use vector diagrams too, but I just wanted to show you that we can do it, and then we'll take a complicated example. Z2 dot square. So that's the kinetic energy, right? And potential energy is because of that spring, right? When there is a displacement in the spring, it gives an opposite force. So let's say I stretch the spring by some displacement, it will always give me an opposite force, restoring force, right? So because of that, we have potential energy, and that is equal to V equals to half K. So total displacement in this will be the Z1 and Z2, right? So it will be Z1 minus Z2 whole squared. So that's the potential energy we have, kinetic energy, and this is potential energy. Okay. So now our Lagrange's function is L equals to T minus V, which is equal to half M1 Z1 dot squared plus half M2 Z2 dot squared minus half K Z1 minus Z2 whole squared. So that's our Lagrange's function or equation, right? So now next step will be to get our equations of motion, which will be first will be d by dt of partial of L with respect to the first generalized coordinates dot, right? So that will be with respect to Z1 dot minus partial with respect to Z1 equals to the force in the direction of that generalized coordinate, which is F1 here, right? Similarly, we can write the second equation. So the number of equations will depend on, So we have two generalized coordinates, there will be two equations of motion, right? So that will be d by dt of partial of z2 dot minus partial of z2 equals to f2. See, if we didn't have any force on second cart, this f2 will be 0. So any combination of these things can be employed, right? So if we do the derivation, like all we need is these two partials here. So everybody good with the differentiations, right? No problem with that. So, so what will be partial of z1 dot? So z1 dot only appears in this term, so it should be just m1 z1 dot, right? And partial with respect to z1, partial of L with respect to z1 equals to, what's that, minus k z1 minus z2, right? Similarly, we have partial of with respect to z2 dot, which is equal to what? m2 z2 dot, and with respect to partial of L with respect to z2 is equals to k z1 minus z2, right? Now we can replace this, just substitute these terms here. So we should get our first equation, which is partial of time derivative of this, right? So that will be m1, m is constant, m1 is constant, so it will be m1 z1 double dot minus this, so that will be plus k z1 minus z2 equals to f1. That's our first equation. And the second equation similarly will be m2 z2 double dot minus k z1 minus z2 of f2. This, ladies and gentlemen, is our equations of motion. What can you say? Yes?
Is it double dot because of the...
Time derivative, yes. So we took another derivative, this one, right? So because of these two, we got the double derivative here. What can you say about these equations here? So if you see, we have inputs in these equations, right? F1 and F2 are the inputs, and Z1 and Z2 are our either generalized coordinates or outputs, if you have a sensor which can read the displacement. And these are differential equations, right? These are second order differential. You guys know differential equations? First order, second order. And we will be like, when we will be doing the math preview, we'll be going over these. How do you solve first order differential equation, second order but that's one type of modeling, right? We have state space, we have higher order differential equations, so that kind of categorizes into higher order differential equations, okay? And then we'll see how we can use it to get transfer functions or state space, that kind of representation. So for now, just hold that this is what we got. These are the equations of motion we got this from our, this is the mathematical model of the system that we have. That now this will be another deal. How do we simulate it and all that stuff? We'll get to that point. But any questions here? Okay. Now you can solve for Z1 dot, Z2 dot, and all that stuff. But for now, we'll just stop here and we'll get back to this when we are doing state space and come back to this example. But how we can use these equations to get the state space equations of the system, and then how can we simulate, put this, because solving second order differential equation is hard, okay? Somehow if we can get it to first order differential equation, then life becomes easier. So we'll get there. Questions? Nope. So let's do one more example. This I could have done directly by comparing the forces. But the second example is called inverted pendulum on cart. And this is the one we will implement. Okay, so let's define our system. We have a cart, right, of capital mass M here, and we have a pendulum. The length is L, the mass of this is small m, and this angle is theta, and this distance is, let's say, z. Okay, so this is, and the only input to the system is a force applied to the cart. Okay, so what we are doing is we are applying a force to the cart and tried. So you might have done this, right? You might have balanced pen. So you have to move your hand or the cart to balance the pendulum. Okay. Later on, we can design controllers to keep this pendulum stable. So this is what we want to model. So first, what is the first step? You want to choose your generalized coordinates here. Okay. So what I see here is, one is the z, which is the displacement of the cart, which is 1 degree of freedom, and another is theta, right? So there are two generalized coordinates here, z and angular displacement of the rod, right? So these are two generalized coordinates we have here, and let's directly get to kinetic energy, Ke, which will be kinetic energy for this mass and this mass, right? So that will be half capital mz dot squared. So that's simple for this because there is only one motion, one side motion, that is z for the cart. So that's not a problem. But this here has motion in this direction and this direction, right? So you can find those two coordinates, x and y coordinates. So we can define this as, let's say we call this as z2, okay? And we can call this as z1. So those are the coordinates of your center of the mass of the bob, right? So what will be z1? Z1 will be z, right? This plus this here, right? So how do you get this part? I know that's z. How do you get this part? That is like project your L to this, right? You can project your L on to that. What will be that? So that's perpendicular to it. So that will be L sine theta, right? So that will be z plus L sine theta. Okay? Questions? Okay, and z2 will be, what is z2? So there is a convention here, which side is positive and which side is negative. So I always consider anything towards gravity, anything coming towards Earth is positive. That's one standard because, okay. So you will be surprised when we do aircrafts. We'll say north, east, down, right? So north is positive, east is positive, and down is like towards the gravity. So when aircraft is flying at a altitude of 300 meters, that will show minus 300. So that's the convention we can apply here. So that will z. So that means z2 will be L cos theta. Okay. So now, what is the kinetic energy? We can add half m z1 dot squared plus half m z2 dot squared, right? So that's the total kinetic energy of the system. That includes your cart as well as the ball. Okay? And so potential energy will be because of just mg. So if you see mg, have you heard of mgh? If so potential energy of a ball at a height h will be mg into h. So that will be mg into L cos theta. Okay. So maybe we'll consider this as positive here. Otherwise, there will be confusion. Okay. So once we get that, we can define our Lagrange's, and then we can find z1. What we need z1 dot and z2 dot also. That we can differentiate these two equations. Yes.
Why is the mass not included in the last one in the kinetic energy? In the kinetic energy equation?
Oh, that's a typo.
Okay.
So, yeah. Okay. Questions? It's very hard to do eye contact with 60 people. You know. Yes.
I guess my question would be, when we're doing, all this fine coordinate systems, the kinetic and potential energy, what are we hoping to accomplish? What are we solving for?
We are solving for a model which relates input to those coordinates, right? If you see those equations in the previous example also, we had z1 double dot plus some function of z1 z2 equals to f. So now we have a relationship where your input and output are related within an equation. So that means that's a mathematical model. We can use that model to say, if I apply this f1 and f2, what will happen to z1 and z2? So that is the goal of modeling, right? So we want to relate u, which is the input of the system, to the output, which can be your z1 and z2. So that's the objective. What is the mathematics which is connecting these two components? That is what we are hoping to get.
Okay. Thank
Yeah,
you.
good question. Okay, so next step, same thing. You have to find z1 dot will be z dot plus L cos theta dot. Remember, theta is now so that, and z2 dot will be minus L cos theta dot. Okay? So you can substitute these terms in here. I will skip the differentiation part now. I will directly write the equations of motion, but you get the point, right? Now we will have to find so the first equation will be d by dt of partial of L. Did I write L somewhere? So my L will be half mz dot squared plus half m z1 dot square plus half m z2 dot squared minus mgl cos theta. Okay, so that's my L. Partial of this with respect to z dot minus partial of L with respect to z equals to the force that I am applying here. Yes?
Can we just go back to the Z1 dot and Z2 dot? So why did you change the sign in Z1 to cosine of Z1 dot?
Oh,
For Z2, should it be L sin theta, sin theta dot for Z2?
Yeah, so this angle is with respect to this, right?
Yes.
So this is the, do you know perpendicular base hypotenuse of a triangle, right? So this is base, this is a perpendicular, this is a hypotenuse, right? So if I have to project, so there's a direct, so when I project h to b, so there is a relation b is nothing but h of cos theta, okay? So there is a,
The question is more so, there's an inconsistency in how just the derivatives between z1 dot and z2 dot. Is that, so should z2 dot be all sine theta or is one not correct?
oh yeah, that's definitely,
It must be positive.
oh, it should be positive? No. No, it's negative, yeah, minus L sine theta. So when you take a derivative of sine, cos, cosine, it's a negative sign.
It was negative first. Okay.
Yeah, sorry, that's my mistake, that's, yeah. Good, you guys are awake. Well, I like it. Yeah, so that's sine theta, guys, yeah. Thanks for pointing that out. Okay. So the next equation will be with respect to theta dot minus partial of theta equals, so there is no torque applied directly to change theta, right? So that's why this has to be equal to 0. There is no as such generalized force for that degree of freedom for theta. Only force that is being applied in the direction of z, so that comes to 0. So we have to find this. You will see that will get complicated. I'll little bit, not that much, but you have to be careful, like not doing this kind of mistake, because then your simulations will be doing a showing bad behavior. Okay. So once you do that, just compute these parts. I will not do the partials here, but I can directly write. Again, we will put these notes as well as the video also. So just in case. So I think you guys should verify this, whether the equations that I wrote matches with this or not. Maybe I can add that as a first assignment. Let me know when we are good to go on the next page. Good? Okay. Equations. Did I lose them? Yeah. So I'll write it again, m plus m z double dot minus ml sine theta dot squared plus ml cos theta double dot equals to f, and ml cos theta z double dot plus ml square theta double dot minus mg l sine theta. Okay, so that's, and again these equations will be used to simulate. So again we have these equations now, and these will go into your computer to kind of mimic the behavior that we have here. Okay, so that's where we will use them. Okay, any questions here? So again, these are differential equations, and so now next type of modeling, which is the for me I think, or in the modern world of computers, that is the best from my point of view modeling system. So that's called state space. Okay. So what we do in state space is the following. So I'll just define what state space looks like. So we have some states of the system, okay? So X is a vector, okay, that defines the state of a system, okay? So as I told, like for example, for a car, right, my awesome car moving, we can have our states as P north, P east, and psi. So that is the north, the direction position, east position, and the heading with respect to. So if I say my car is moving in this direction, right, with the velocity vector. So this is P north, P east, and this is the heading with respect to the north. So that these three states I have chosen, which defines my system and the trajectory of the car or something, okay? So that's the first important. In state space, you need to identify states of your system for a, like it can be hot and cold kind of states, angry, not angry kind of state, and in car we have position. So that's very important. So we always say that our states X belongs to Rn. What does that mean? That means it's a vector of, so there can be n states, okay? So X can have n different states. So X represents the total states of the system, okay? Rn means it has n state, that means x1, x2 to xn, okay? And that's one thing. So another thing is U, okay? U is again the input of the system. So you have, and these states are internal, they does not have to be output of the system, okay? So these are internal states, somehow related to output, of course. And U is, of course, your input. We say that there are k inputs to the system, okay? K inputs to the system, which is U1 to UK, okay? So, and the third thing that is Y, which is the output of the system. Again, so again, we are talking that this is U, this is Y, right? And there are states inside it, that is the internal states X of the system, okay? That's what three things that are needed to define a state space model of a system, okay? So, and that Y will be again, I can write somewhere here, Y belongs to Rm, which means it's a m-dimensional vector, which is Y1 to Ym. Okay, you got it? So we have n states. This will be our convention throughout the course. We have n states. N can be 1, 2, up to whatever. We have k inputs, right? In case, and we have m outputs. Okay, so this is how we define a state space of the system. Okay, so the next thing we need to complete this is we want to find out how these states are changing with time. Okay, that's important. I gave you states and input and output vector, but now I need a relationship. How are these states changing with time? Because that's the modeling part, right? That's the mathematical model. If I know how my states are changing with time, that's right. So what you do is you define n first order differential equations. Okay, you get for each of these states, you find what is x1 dot, what is x2 dot, okay, up to xn dot. So that's the next modeling part. Okay, we have to get, so state space is nothing but n first order differential equations. So you choose your states and then each state has a differential, first order differential equation associated with it. And I'll get, once we apply this to the pendulum example, it will be much. Okay? So now, so that thing can be written as a function, f of xu, right? Because this each first order differential equation will depend on its own state and all the remaining states, okay? Which can be written as n differential first order differential f1 of xu, f2 of xu, fn of xu. Okay? Similarly, your output y is also function of states, which is a function h of xu, which is m function h1 xu to hm xu. So now modeling, basically this is called the output equation, this is called state space equation, and now the objective is to come up with these n first order differential equations. N first order, and solving first order differential equation is much easier thing. You will realize that later. First order differential equations. That is the objective. We have to find n first order differential equations. Okay, so this will apply generally to every problem that we'll be doing throughout the course. We will have a UAV which will have 12 states. P and P, PD, so the position, then velocity, then attitude, then the angular rates. So 12 states. So we will need 12 equations of motion, 12 first order differential equations. So that's how we will be dealing, because once we get differential equation for each first order, we can solve it and say what is the relationship, how the states are varying with the time, right? So that's the goal we have. Now we have to, first step is identify what are the states, what are the inputs, what are the outputs, and then come up with these first order. Come up means use like Lagrange's method or Newton's law to come up with these differential equations, okay? And it will be clear from example how we will come up with these equations, but that's how we will model a system in a state space form, okay? Questions here? So let's just quickly go back to that two train problem and see if we can do the state space there. Do you guys remember the equations for two train? So for the two-car problem, right, you have, so we had m1 z1 double dot equals to minus k z1 plus k z2 plus f1, and we had m2 z2 double dot equals to k z1 minus k z2 plus f2. Okay, so this was this is the second order differential equation we derived from Lagrange's method, right? So now objective is, okay, let's put it into state space form. So the first objective is to get your states, x. Okay, so we can say that, let's say position and velocity of each cart is kind of a state for the system. And you will see why I chose, it will be clear. You can, again, choosing states is not unique. It depends on what problem you're doing. You can choose the difference of positions as a state or whatever, but the number of states generally remains same, number. So if I have 4 states, even if I change states, the numbers still have to be same. And it will be clear later on when we do the proper math about it. But let's say I choose states as, my first state is Z1. Okay, my second state is Z2. And then Z1 dot and Z2 dot. Okay, so the position and velocity of each cart is your state. Okay, and what is my input? U, which is F1 and F2. So that's no problem. And let's say you have a magical sensor which can read Z1 and Z2. right? So your y is z1 and z2. So now you can see what is n here. What is the dimension of vector? 4. So n is equal to 4. We have 4 states. How many inputs? K equals to 2. We have 2 inputs. How many outputs? M equals to 2. We have 2 outputs, right? So now the second part is, now let's get the equations of motion. That is the first order differential equations for each state. So what is z1 dot? So the first is z1. So what will be z1 dot? So this is like x1, x2, x3, x4, right? z1 dot, or I would say x1 dot, is nothing but x3, right? x1 dot, which is z1 dot is nothing but this state. It's a state. It's the third state in the system. So all I'm trying to find is how how each time derivative of each variable is related to the state. So my z1 dot is the third state in the system. This is z1 dot, right? So x1, because this is x1 dot is x3. What is x2 dot? x4. No problem. That's the equation of motion we have. What is x3 dot? Because we need, which is z1 double dot. We can solve it from here, right? We have a differential equation which relates z1 dot to these things, right? So what will be that? That will be minus k by m1. What is z1? x1, right? Plus k by m1. z2 is x2. Plus f1 is u1, I would say, the input one, u1 by m1. So that's x3 dot, and our x4 dot will also be similar, minus k by m1 x1 minus k by m2, oh sorry, this is m2, x2 plus u2 by m2. So we have 4 first order differential equations. Now if you see, we know how each state vary with time, as well as how it is related to all the internal states as well as the input, right? Now we can solve, like we know how to solve first order differential equation. We will put this in MATLAB or any ODE solver, and it should give us a output depending on what your initial conditions are and what your input. So we'll take this in the next class from here and show you how we can use MATLAB Simulink first, and then later on in the class we will go and do a tutorial on what ODEs are, what matrices are, because you will see the matrices will come out of it and everything. But I will put these notes and this video online tonight. And okay, so next class, if you want to bring your laptops, if you have MATLAB, bring them. Thank you. So, where are my equations of motion then? Which is this: small m plus m z double dot minus ml sine theta dot square plus ml cos theta double dot equals to f, and another equations ml cos theta z double dot plus ml squared theta double dot minus mg l sine theta equals to 0. So these are the two equations you get after you plug in the partials in those two equations. Okay, again, so these are what? These are differential equations. These are second order differential equations again. Okay, these are second order differential equations. And right now it might not be making that much sense that, okay, now what, so what kind of question might be coming in your mind that, okay, we got it. Now, what does, I don't know if I can see these equations and make any sense that what is going to happen. So that's the good thing. What we will learn is later on, we will put them in that form so that we can see and tell, oh, this system is stable. Oh, if I do that, this is going to happen. So those will be the next steps here, but this is the first model type of modeling that we get some differential equations which connects your input to the output. That's all what the take-home message here is. Okay, that we have second order. So this can go third order, fourth order, depending on what kind of system you have. But here we have second order differential equations. Okay, any questions? Yes. Could you go back up a little bit? In the previous page.